Thank you, thank you. All right, so let's just take a look at this first reaction. This would be how we halogenate a benzene ring. In all of these reactions, what role is benzene playing?
Nucleophile.
Nucleophile, right? So that's everything that we've learned up until this point. Benzene is playing the role of the nucleophile. And then what is our iron 3 bromide catalyst doing for us?
It makes the electrophile.
It makes bromine an even better electrophile, right? Because benzene is playing the role of the nucleophile, but it's not a particularly good nucleophile. So in all of those reactions that we learn, we have to prep our electrophile, right? To make it an even better electrophile. Awesome. So first reaction, that's how we halogenate a benzene ring. If we want to focus on this one right here, this would be called nitrating the benzene ring. This is what sticks a nitro group on there. And then remember, and this is something that's going to be really, really important to keep in mind, we can convert a nitro group to, does anybody remember what the heck that's called when you have an amine on the benzene ring?
Aniline.
Yeah, you can convert your nitro group to an amine group, making aniline by having the reducing agent H2 and palladium catalyst. Okay, and again, this is going to be something that's sort of key. We're going to see even more stuff that you can do with these amine groups here later on in this chapter. So keep this reaction in mind. It's pretty important. Now, the other two, let's get to our last two boxes that we haven't solved yet. For this, we have to remember that there's this idea of once we have a substituted benzene ring, right? So I have something on there that can direct the next substitution to different positions. And remember, we had these like fancy Latin words for those. Right next door are the ortho positions. The next ones are the meta positions. And then on the opposite side is the para positions, OMP. Okay. The nitro group, is that going to be electron donating or electron withdrawing?
Withdrawing.
Going to be withdrawing. So withdrawings are what type of directors?
They're meta directors.
So they're meta, yep. So for now, you guys can sort of use this cheat sheet, but of course, this is going to be what you need to have hammered into your brain for the exam, right? Withdrawing, they are deactivating, and they are meta directors. Electron donating groups are activating, and they are ortho-para, right? So our nitro group here is deactivating, so that will be a meta director. Whereas our amine group is activating and an ortho-para director. So here we would have a mixture of products. One being our para, our ortho, and the other one being the para-directed product. All right, so you get a mixture of both of those.
The one on top is the benzene ring, with the molecular bromide and the iron bromide. Would that one just be the bromobenzene? That wouldn't be a mixture of products?
Would you, are you saying like, why don't I have a di-substituted or a tri-substituted or whatever?
No, I mean like it's just bonded to one carbon, but it wouldn't, oh, well, I guess it wouldn't be, never mind.
Yeah, right, because when you have, yeah, no, and it's a good question. It's basically the ortho-para meta, they only pertain to benzene rings that have two substitutions, and they're indicating how far apart they are. So even when you get to three substitutions, you don't even really, you know, the terminology doesn't work quite that well. But yeah. So yeah, I think you got your own thing. But yeah, so this is this idea, and I think that you guys can see sort of where this level of complication is going, right? Because again, I can then take the, if I really wanted that meta substituted product, I could then take this and add my palladium catalyst and H2, and that's how I would be able to form the meta alanine, right? So you can see the sort of like levels of complication that are going to arise from having these directed sort of substituent groups. Okay. So then I think somebody asked me last class, I don't remember who, but there's a sort of the next logical question is when you have your ortho products and your para products is, you know, what's the distribution there? Are they actually going to be a perfect mixture? What plays into that there? So that's where we're going to pick up today, talking about what sort of would determine the ratio of your ortho and para products. Okay, so here we're going to nitrate our, this guy was toluene. We have a methyl group. What type of director is that? Is it electron donating or electron withdrawing?
It's an ORTHO-PARA.
All right, so this one is slightly donating, and so it's an ORTHO-PARA. I think that, you know, there's a reason why I kind of hammered this portion, trying to like embed that into y'all's brain, because I think it's very difficult to try to memorize this list, right? I think the easier thing to do is to look at your functional group and assess whether or not it's donating or withdrawing. And then from there, you would know donating equals ORTHO-PARA, right? So yeah, I don't know that I would try to go like memorize that list. Okay, so we have our toluene. This is going to be ortho and para directing. So can anybody like think of one reason that one of these products might be preferred to the other? Remember, here is my ortho sites. I'll label them O. And then down at the bottom here, there's my parasite. So there's two big factors that are going to play into this. Can anybody think of what one of them might be? What about this ortho position located right next door? What problem might we have if we have, let's say, a really big functional group there?
Steric hindrance.
Sterics, right? So that magic word, sterics. So that's going to be one of these factors that are going to come into play is your ortho site sterically hindered? And then there's another thing that actually favors the ortho site, right? Makes it more statistically more favorable. Can anybody see what that would be? If this is just a numbers game.
Wait, I'm sorry, what was the question?
There's actually another factor that plays, so steric hindrance is one of them. There's another factor that's going to come into play that actually favors the ortho site over the parasite.
Because there's two ortho possibilities.
Boom, nice job, Jesse. Absolutely. So if it's just a numbers game, you have more ortho sites than you do parasites, right? So if steric hindrance wasn't a factor, you'd actually expect to get twice as much ortho product as you would your para product. So these are the two things that are going to come into play. So if we have a nice tiny group, a nice tiny methyl group, we would expect something very close to that 2-to-1 distribution of ortho to para, right? So if it was perfect, it would be 66%. So there's clearly some steric effects going on, but it's close to that. You get more of your para product. As the number, as that substituent grows, it's going to change that distribution because of steric hindrance. So now if instead of a methyl group, we have an ethyl group, now we're down to a 50-50 distribution. And then if we have something huge like this big tertiary alkyl group here, this gets us very little of our ortho product, and we see more para products because of that steric hindrance. Okay, so two main factors that you have to worry about. The first one is the 2-to-1 ortho to para sites. All right, that's the fact that you have more ortho sites. So if this is a numbers game, you'd expect to have more ortho products. And then the second factor being sterics. All right, so that's what's going to influence our ratio there. Okay, so now this section is, I think, kind of a bummer of a section. I think this should be called, it's like additional considerations regarding substituent effects. It should be called like kind of the exceptions to the rule sort of things. So let's just go over that real quick. First of all, this idea of activating versus deactivating, right? We said that electron donating groups are activating and electron withdrawing groups are deactivating, but what does that mean exactly, right? So again, the idea is that substituents like this group right here, where my oxygen can donate electrons to that benzene ring, makes them an even better nucleophile. And so some of these reactions will proceed faster than if you just had like a naked benzene ring all by itself, all right? In particular, the halogenations. If you have an activated benzene ring, a strongly activated benzene ring, so there's an oxygen that can donate electrons or a nitrogen that can donate electrons, these can be halogenated without a catalyst. All right, you've activated that benzene ring to the point where it's no longer a crappy nucleophile, it's a good nucleophile. And so now it can react just with bromine on its own. And of course, because it's an activating group, it's ortho-para directing. If you do have a catalyst, so if you did carry this out with a catalyst, you would end up getting all three, you would end up substituting all possible ortho-para positions. All right, so now let me really quickly go back and revise the example that I did at the beginning, because here we did have a strongly activating group, and I'm gonna have to just remove this catalyst because I only want one substituent. Oh, otherwise, if there was the catalyst, I'd have to put all the benzenes in there. Okay, but let's just update the example that we did so we can be extra good when we look back at our notes. Of course, this doesn't apply to the above group, the nitro group, because that was deactivating. So you still need a catalyst, right? It's an even worse nucleophile than when you have just the naked benzene ring. All right. Other exception has to do with these Friedel-Crafts reactions, right? So these were these acylation and alkylation reactions where you had aluminum chloride. What was the aluminum what was the aluminum chloride doing for us?
It helped generate the electrophile.
Yeah, and what did it specifically, what was it doing?
It would bond to the chlorine.
Bond to the chlorine and chop it.
Yeah, chop it, yeah. It would take it away.
It was, yeah, absolutely, right? So this gets rid of this chlorine and replaces it with the carbocation. Same thing when you had an acyl chloride, and then we called this an acylium ion, right? But remember, that's the role that this aluminum chloride's been playing, is it literally plucks off that chlorine. Okay, so that's all well and good when things are normal, but what happens when we have metadirectors, right? Remember, metadirector is synonymous with deactivators. So it turns out that these Friedel-Crafts reactions were by far the slowest of all the electrophilic aromatic substitution reactions that we learned. And if you add a deactivating group onto there, they're just so slow that there will be no reaction that proceeds. Okay, so you cannot perform an acylation or an alkylation on a benzene ring that's been substituted with a deactivator, with a metadirector. All right, these reactions are just so slow that they basically don't happen. If there's an activator, you're all good. Ortho-para directors, you're all good. But if there's a metadirector, there will be no reactions of the Friedel-Crafts kind. All right, so again, another important exception to remember here. And the last one involves aniline. Okay, also pertaining to those Friedel-Crafts reactions. The problem here is that nitrogen will interact with that aluminum chloride. So you can't have a normal old Friedel-Crafts reaction with aniline because your catalyst ends up reacting with that amine group on the benzene, on the aniline. Okay, so these are another compound that is not going to be able to be alkylated or acylated, right? So no meta-directors and aniline have to be crossed off your list of possible reactants for the Friedel-Crafts. Okay, and then the last one here is if you wanted to nitrate an aniline, so stick a nitro group on there. The problem with that is that again, your in this case, your nitric acid will actually oxidize the amine. It will react with the amine instead of reacting with the benzene. We can get around this though. We can do that by converting our amine group to, what would this be right here? Specifically, if we look on amide, absolutely. So this is again one of these protecting group type strategies. All right, we have to protect our amine group by converting it to an amide, and then we can go ahead and nitrate our benzene ring like normal. All right, so that gets us to here. This is just our normal old nitration reactants that we need. And then we can remove that group with an acid catalyst and heat, followed by base. All right, so this is, again, if you want to nitrate your aniline, you have to jump through some hoops first. You have to add this protecting group. Specifically, you have to convert it to an amide by adding in an acyl chloride. Remember, this is back chapter 16 business. Acyl chlorides will react with amines to create amides. So that's our strategy here. And again, it's this idea of a protecting group. Okay. So the last thing here now is this is now sort of playing with this idea of your different substitutes here. Basically, what we're going to find is because certain substituents are ortho-para directing and other ones are meta-directing, the order in which we combine these reactants becomes very important for the product that we want. So everybody take a second and see if you can't figure out how to create the meta-bromobenzene sulfonic acid here. All right, first of all, you got to start with, how do we stick a sulfonic acid group on there?
You add sulfuric acid?
Yep, just sulfuric acid. It's really, that's all you need. It's both the catalyst and the reactant.
Two of them, right?
Yeah, the two, one of them, well, so one of them's going to be consumed and the other one's not. So you just need to have a slight excess of the sulfuric acid, right? So catalysts don't actually get consumed. But yes, this is how we would go about sulfonating a benzene ring. And then we did some examples previously where we know how to brominate a benzene ring, right? But the question is if I specifically want the meta product, how am I going to have to do this? All right, so everybody take a second and see if you can't figure out how that would go down. Keeping in mind, if I had an SO3H group on there, would that be donating or withdrawing?
Withdrawing.
Yes. All right, so first we would add our sulfuric acid and heat. That is going to be adding that sulfonic group on there, and that is a strongly deactivating, thus meta-directing. So then if we added our bromine, why do we have to make sure to include the catalyst?
Because it's a meta director.
Because it's a meta-director, right? So deactivating, absolutely. All right. So now what if we want the ortho and para products? So for this, I want to go back to this list real quick because I should have done a better job of pointing this out, but honestly, I kind of missed it at first too. Let me get rid of my markings on this list here because it's a little busy. Your halogens. All right, they're sort of weird in the fact that they are considered to be weakly deactivating, right? Remember, deactivating because they have this induction effect where they can remove or sort of withdraw electrons because they're all very electronegative. Nonetheless, they are still ortho-para directing. They do still have electrons that they can donate to that ring, which I'm guessing is what the fact that they are ortho-para directing. Okay, so they're a little bit weird in that they are deactivating but still ortho-para directing. All of our other deactivators are meta-directing. Okay, so make sure to keep that in mind. Our halogens are actually ortho-para directing. Okay. So then if we go back to our synthesis problem here, now if I wanted that ortho-para product, I would have to reverse my additions that I did, right? I couldn't sulfonate first because that would give me my meta product. So the first thing I have to do is add my bromine, get bromobenzene, then I can add sulfuric acid and heat, and that would direct to the ortho and para sites. All right, so this is a pretty simple example, but you can see sort of the multi-step synthesis type problems that we're going to have here. Okay. All right, so now what happens when you have two different groups? All right, so everybody take a second and figure out which site these two groups would try to direct to. You can just sort of mark it on your benzene ring here. All right, sorry, I was taking notes. All right, so first of all, we have our methyl group here, activating or deactivating?
Slightly activating.
Slightly activating.
Deactivating.
Oh,
Deactivating.
no, methyl groups will be activating.
Okay.
Right? They can add electrons not through normal resonance means, but through that hyperconjugation. So these would be ortho and para directing, although the para site's currently occupied. And then what about our nitro group here? This is like
That's
the
deactivating.
quintessential strongly deactivating group, right? When you think deactivating, nitro group should be the first thing. That will be meta-director, but of course meta-directing relative to that nitro group are those same two sites, right? So in this case, this is kind of your best case scenario here, where both of the substituents end up directing to that same position, and thus you will get substitution on that position. Okay. Same thing in this example here. All three of both your methyl group and your halogen are ortho-para directing. So that's directing to those same sites. And so you would get a distribution of products with substitution at those sites. Right, so this is kind of the easiest case scenario where you have two substituents, but they're both directing to the same position. Awesome. All right, so now clearly we're going to make it a little bit more difficult. What happens when we have directors that are directing to different positions? So for example, here we have an OH group. What's that going to be? Ortho-para or meta?
Meta.
No. Right?
Ortho.
Ortho-para. So what you want to do, you look at your substituent. Does it have electrons to donate? If it does, then it's an activating group, right? A donating group is ortho-para. So your hydroxyl group is going to want to put the substituent there, the bromine there, but then we have a methyl group down here, and that wants to direct to its ortho sites, which are there, right? So which one's going to win? This is where you have to consider our little ranking here, right? This is why we went and distinguished between strong activators, moderate activators, weak activators, et cetera, et cetera. Whichever one is the stronger one is what's going to win. So in our example here, the hydroxyl group is a strong activator, whereas our methyl group is a weak activator. So the hydroxyl group will win, and our major product will be having substitution at that hydroxyl group's ortho position. All right, so again, now we have sort of a conflict between our two substituents, and the question is which one's going to win. Again, it's going to be whichever one's the stronger one. And then if we have the last sort of situation here, now we have a methyl group versus an ethyl group. Again, methyl group, weak activators, so it wants to direct there. The ethyl group, also weak, wants to direct there. In this case, nobody's stronger than the other one, so you will have a mixture, more or less 50-50 distribution of your two products. Maybe would expect slightly less of this guy here because again, you have that steric effect going on. All right, but those are your considerations. If you have two substituents, you got to look at where they're going to direct to. If there's a conflict, which one's stronger? Okay. All right, so this is the last thing that we got to cover here, more or less, and it's going to be something that's quite powerful in terms of our multi-step synthesis here. Again, I told you that aniline was going to play a bigger role in the rest of this chapter today, and that's indeed the case. That's because if we take our aniline and we combine it with this sodium nitrate here, nitrites here, we will get called a diazium salt. All right, and notice that this is now NO2, not our HNO3 that we were using to nitrate it before. It's a pretty minor mistake in the scheme of things, but just something to watch out for. So this isn't, we don't really care about getting our diazium salt as an end product here, but this is really important because it now opens up a new type of reaction. That diazium group is actually a really good leaving group. So what happens is if I take my benzene diazium and I combine it with a nucleophile, I can get nucleophilic substitution of that diazium group. All right, so basically we're gonna be introduced to a series of reactions here where first we convert aniline to this diazium salt, and then we do a nucleophilic substitution, substituting that diazium group for something else. Importantly though, everything that we learned, like you need to put a divider in your mind right now. Everything that we learned previously, benzene was playing the role of a nucleophile. Right? Now these are going to be reactions where we have a nucleophile that's going to be substituted to our benzene ring. Everything else we were doing, we were substituting electrophiles. So this is how you add a nucleophile to your benzene ring. Okay? And again, it's because this guy right here is a great leaving group. It will pop off as nitrogen gas. Nitrogen gas, very entropically favorable because it's a small gas molecule. It's also got an incredibly low free energy, right? So replacing that, so having it be whatever, basically it's a really good leaving group.
What does the arrow on the N2 mean?
To be honest, that's in the book. I assume that it means that because it's a gas, it leaves.
Oh, okay.
But honestly, I'm making that up because I've never seen it before. But that was my interpretation. All right, so again, these are going to be all about substituting that diazium group. Okay? For these, so you can, one of the easy things to do are to use these copper salts. It's interestingly, they have no idea why copper salts work so well, but they do. But anyways, I'm talking about having, really my nucleophile here is going to be this bromide ion, this chloride ion, or this cyanide ion, right? It's just in compound with this copper. And again, these are substitution reactions. You're going to be substituting your diazium group for the bromine group. Likewise, when I add copper chloride, I will get a chlorine substitute. This is a good way to put a nitrile group on your benzene ring, right? So this is now, again, just to sort of clarify the grand scheme of things. Before we learned about how we add electrophiles to our benzene ring, these are all about how we substitute on nucleophiles. One of the good news, you don't have that same problem of having to worry about ortho-para meta-directing type of things because you're always substituting out that azium group, that diazium group. So wherever that was, that's what's going to be replaced. You don't have to worry about directors in these type of reactions. All right, so those are, we can, so also if you wanted to add iodine, you could use potassium iodine. Fluorine, you actually have to use this borofluoride. And then there are two different ways that we can generate a phenol. Kind of the most straightforward is to just add acid and heat. Unfortunately, the book makes us learn another one because in practice, that's not the most efficient reaction. If you really wanted to do it, you would use this copper 1 oxide. And that's how you would very efficiently create a phenol group on there. There's one more reaction that I want to add on. It wasn't in the slides, but I think it's really, really important. It's in your book. And that's how you chop off that azium group altogether. Okay? So for the sake of like having room, I'm just going to replace one of these existing reactions here. All right, so now if we want to just chop, well, come on. If we want to chop off that group altogether, we use this, gosh, what was it called? I don't know, phosphonite acid or phosphonic acid. So not H3PO4, which is the one that we're used to, but H3PO2. And again, this has the effect of just chopping off that azium group altogether. Diazium, sorry. Okay, so this is kind of important. If we want to just go back to our example here, we learned how we could take a benzene ring, convert that to a nitro group, and then convert that to an alanine. We now see why that scheme might be really important because we know how to convert that alanine to now this diazium and do substitutions with it, right? So this scheme that I've highlighted here might be that much more important in our multi-step synthesis. There's no way to go back unless you chop off the azium group and then add a nitro group on there. All right, so you can't actually just go in this direction here. You got to go all the way back to the benzene ring by chopping off that group. Okay, cool. So any questions on that? So last thing here is to talk about the effects of these substituents for now our nucleophilic aromatic substitution reactions, right? So one of the things to keep in mind is that before we were talking about nitro groups as deactivators because they were withdrawing electrons. That was in reactions where the benzene ring was playing the role of the nucleophile, right? So withdrawing electrons from that benzene ring makes it a worse nucleophile. When we're talking about these substitution reactions, benzene's not playing the role of the nucleophile, it's an electrophile. So the nitro groups have the exact opposite effect, right? These now electron withdrawing groups make these more reactive. So for example, we can do nucleophilic substitution reactions on halogenated benzene rings by just adding base. But we're going to see that the conditions get, you can do so with less harsh conditions if there are more nitro groups on there. So for example, if we want to look at this top reaction here, again, I'm going to nucleophilically substitute out that chlorine for that OH group.
Wouldn't that still be a para addition or substitution?
Yeah, okay, so again, this is where you want to keep these things in your mind, like sort of separated in your mind. That ortho-para meta business, that was only for when benzene's playing the role of a nucleophile. When you're talking about these substitution reactions, you don't have to worry about it because you're going to swap out whatever that group was. Right? You're not substituting a hydrogen anymore. You're replacing whatever that good leaving group was on the benzene ring. So you don't have any sort of ortho-para business to worry about. That's only when benzene's playing the role of the nucleophile. All right, so again, and if I wanted to, we can, right, just sort of convince ourselves that we know how this would go here. We have our OH group that would attack and eventually be swapped out for that chlorine group. We'll get to reaction mechanisms more specifically here in a second. Of course, resonance is going to play some role, but this is all we're talking about is replacing, substituting a chlorine for an OH. So if I wanted to do that on a benzene ring that has one nitro group, I got to take that all the way to pH 14. Incredibly, incredibly basic conditions and a temperature of 160. Right? Really very hot, right? So these are what we would consider to be extremely harsh conditions. Well, if I have two nitro groups on there, their electron withdrawing ability is just that much greater. So I can do so at a pH of 10, and now I only have to take it to 100 degrees. And lastly, if I have all three nitro groups on there, you can do this at a pH of 7, so just using water. You don't even have to have a basic solution anymore, and heating it up to 40 degrees Celsius. So that's, 100 degrees Fahrenheit or something like that. Not that crazy hot, right? So before, we saw that our nitro groups were deactivating for electrophilic aromatic substitution reactions. They have the exact opposite effect for the nucleophilic aromatic substitution reactions. Okay, so now in terms of mechanism, let's just look at what this would look like real quick. See why exactly that nitro group has the effect that it does. So of course, reaction mechanisms are all the same in that you have an nucleophile attacking an electrophile. You just got to make sure you know who's who, right? Again, everything we saw before, benzene was playing the role of the nucleophile. Here we have a nucleophile in this reaction, and so benzene is going to be our electrophile. So the first step is that you have your nucleophile attacking that carbon that contains your leaving group. And now benzene is going to do its thing where it's going to distribute that charge around the ring, right? So that charge will first be isolated on one of those carbons, but again, this is all in resonance with one another, so we can bounce that around our ring. As such, right? So here are all our different resonance contributors. The big one, of course, being this guy here, all right? I guess this sequence of events here. This is how this nitro group is able to stabilize these intermediates, making this reaction more likely to occur. Right? Because you have that carbanion with a negative charge that's going to be located right next to that nitrogen that has the positive charge, and it can share that pair of electrons with the nitrogen, right? So you have now an additional resonance structure helping to stabilize this reaction, the intermediate of this reaction. Apparently it's got a fancy name, the Meisenheimer complex. Clearly some German scientist discovered it. We're not going to worry about that. All right, and then the last step here, let's just take note, is that leaving group leaving. So that's how we have our substituted benzene ring. All right, and NAS, again, you're going to see this all over the slides for the nucleophilic aromatic substitution. You want to do everything in your power to keep this in a separate place in your brain than those electrophilic aromatic substitution reactions. All right, and last one, you know, just two other examples to look at here of other things that we can do. Again, these are going to be benzene rings that have nitro groups on them. So they are primed and ready to go for these nucleophilic aromatic substitution reactions. We know that these alkoxide ions are really good nucleophiles, so we can use these as well. As well as amines we know can play the role of a nucleophile. These can be substituted out as well. If you just have your amine and apply heat, you'll actually get a salt, an ammonium salt. And so then you would have to apply a base to remove that proton, deprotonate that nitrogen. But that's how you can stick now an amine group on that benzene ring. All right, and again, these are all because these benzene rings are primed and ready to go for nucleophilic aromatic substitution because they have those nitro groups on there. All right, and then just for fun, what's going to happen if I take this and apply hydrogen in the presence of a palladium catalyst? Anybody?
Would it just be a benzene ring?
No, no. So this is key because so nitrogen in the palladium catalyst, that doesn't chop off any nitro groups or anything like that, but it will reduce a nitro group to an amine group. Right? If I wanted to chop this off, I'd actually have to first go ahead and create it to that diazium salt. And then from here, I can add my, I don't remember the name. It's like phosphonuric acid. I don't remember. Anyways, that's how I would have to chop that off if that was my end goal. Okay. All right, so that's all I got for you guys today. That does it for chapter 18. Again, remember the homework's been posted. That is going to be due next Wednesday for this chapter. Yeah, I think that's it. I think that got it all covered, right? So next week we just pick up with chapter 19. And yeah.
When is the procedure due for the next experiment again?
For 39, it's due on Friday. For 41, it'll be due next Friday. Okay. Yeah. Anybody have any questions on chapter 18 stuff? Again, the biggest advice: keep those electrophilic aromatic substitutions and the nucleophilic aromatic substitutions in different places in your brain. Right? There's sort of two different categories of reactions that we learned about. Only one of those, the electrophilic aromatic substitution reactions, do you have to worry about things like ORTHO-PARA directing business. Cool. All right. Awesome. I am going to go walk the dog and then enjoy my birthday. And I hope you guys have a good weekend. And yeah.
Happy birthday.
Thank you. Thank you.
Happy
All right,
birthday.
I'll see you all next week. Have a good one, guys.